All right, good afternoon, everyone. Thank you so much for joining our first of the afternoon sessions today. My name is Joshua Rasera, and I'm the chair for this session on regolith properties and dust. So without any further ado, I'd like to introduce our first speaker, Tehya Birch from ETH Zurich. So please take it away.
So until the presentation comes up, thank you everyone for joining. My name is Tehya Birch. I'm from ETH Zurich and Airbus Defence and Space. Today presenting on universal predictors of regolith behavior, a universal tool for designing lunar hardware. So I'll go into some details on ISRU and ROXY. ROXY is the regolith to oxygen metals conversion, a process for extracting oxygen and metals from lunar dust. And I'll present the overall roadmap for ISRU production from Airbus' point of view. The first thing that we have to overcome when dealing with regolith in terms of, let's say, extraction of oxygen and metals is the regolith challenge. Hence the session today. And for the ROXY process, we need to overcome this specific challenge, but we went one step further and developed a universal solution for a specific problem, but also for universal application for lunar hardware. I'll go into the methodology in detail and then give you an update on the status. Here we can see the lunar ISRU roadmap as envisioned by Airbus. As I mentioned before, ROXY is the regolith to oxygen and metals conversion process using molten salt electrolysis. Georg Pöhler from IFA Fraunhofer will present more details on our demonstration mission that we're preparing for the moon called Mini ROXY, and he'll be presenting that tomorrow morning at 9 a.m. and he'll be happy to see many of you there. Today, though, I'll be talking about regolith, and the fact is, if we want to use regolith as a feedstock for ISRU, specifically for ROXY, but any other, let's say, extraction purposes, we need to overcome the challenge of how to handle and how to deal with the regolith. Specifically, in our case, we call this a mini ROXY funnel. So this is the receiving end of the payload where regolith is being delivered to the facility through a so-called funnel. It's actually a lot more complicated than just a simple funnel. It's designed to receive lunar regolith. There's a rough size sorting entailed with the sieves to sieve out the larger particles and only to allow the smaller regolith particles to enter the ROXY cartridges where the electrochemistry will happen. There's also the regolith dosing into these individual cartridges, and the whole system is relatively complex, and given the nature of regolith, which is a nuisance to handle and largely its properties are unknown, we need to first overcome the challenges of how to handle regolith before we can think of designing such a complex facility. We heard the sessions in the morning. Regolith is a real nuisance. It's abrasive, it's heterogeneous, and it's got a very complex mechanical behavior. So far, we don't know so much details about how its mechanical behavior works, especially when in interaction with equipment on the moon. So specifically, we need to understand how its, let's say, micro properties influence the macroscopic properties and how those influence its mechanical behavior. How can we transport and handle and process regolith so that it will work with demonstration missions, but also for the future of the lunar ecosystem? It's not only the regolith particles themselves that are complicated and difficult to handle, it's also the harsh lunar conditions that we need to take into consideration as well. The overall regolith particles, they were obviously produced on the lunar surface, subject to these environmental conditions, but also any equipment that we have on the moon will be subject to these as well. So we need to consider how to design the lunar infrastructure or hardware so that it will interact well with the regolith, but also with the complex and the harsh lunar conditions as well. So coming back to the mini ROXY funnel, Mini ROXY as a lunar demonstration mission needs a pre-flight validated regolith loading system to de-risk the lunar mission in general. This is just specifically for Mini ROXY, but if we think of any other, let's say, lunar demonstration mission or lunar architecture, this will have to happen as well. The goal was to create a universally applicable engineering tool for lunar hardware. So we used the specific problem of the mini ROXY funnel and designed and came up with a methodology that's universally applicable. And this is called UPREB, Universal Predictors of Regolith Behavior. And I'll go into some more details on this now. First of all, we need to understand and predict the behavior of regolith in interaction with equipment in order to design successful lunar equipment such as the mini ROXY funnel. There are several ways to do this. One of the disadvantages is that we can't just go to the moon and test the facility on the lunar surface. This would be extremely expensive and unfeasible, so we need to find other ways to do this. Due to the computational advantages that we have nowadays, one way to do this is through simulations. There are two different ways that we could do this. One would be the high-fidelity DEM simulations. These are physically accurate at the single particle level, but their disadvantages is that they're extremely computationally intensive and unsuitable for larger simulations. On the other hand, we've got the empirical and analytical models, which are fast and established for larger simulations, but they're relatively inaccurate since they can't physically simulate the particle interactions on particle level and are unsuited for such high-fidelity experiments. This is a gap in the middle, and with UPREB, we intend to bridge this gap between the high-fidelity DEM simulations, but allowing larger simulations and larger lunar hardware development. It combines this accuracy on the single particle level, but enables these larger simulations specifically for engineering tool. It's physically sound in two ways. It's based on the discrete regolith particle properties, but it's also based on the discrete element method on cores. However, we've gone one step further and enabled the DEM simulations to not only be on a smaller level, but also to extrapolate this to larger simulations, enabling the fast design iterations. Again, it's also not limited to only mini ROXY. Mini ROXY is a first validation experiment for this, but in the future, we intend to have this as a universally applicable tool for any lunar hardware. So now let's go into details on what UPREB is. UPREB is based on 4 pillars. The first pillar is the discrete regolith particle imaging, where individual regolith particles are imaged in 3 dimensions and a regolith digital twin created. In the second pillar, the digital particle property analysis analyzes these 3D images of the regolith particles and calibrates a particle generator to generate, say, digital particles for uses in simulations. The third pillar is the bulk regolith physical properties, where we don't only need to understand how the particles look like themselves, but we need to understand the physics and the physical behavior of the particles, of the bulk regolith. The fourth pillar then is the interaction with hardware specifically. So these would be experiments in the lab to validate the simulations that we do in the third pillar. Going into more details on pillars 1 and 2. The particles are imaged via X-ray microtomography. So far, 12 simulants, regolith simulants have been imaged and reconstructed in the computer. The statistical property analysis extracts individual properties of these simulants, mechanical properties primarily, and compares the individual properties to each other also via multivariate analysis and comparative experiments. Overall, the goal is here to create a digital regolith twin, and this is based on statistics. So we don't want to create an exact replica of individual regolith particles. We want them to identify the key regolith particles, form the mechanical behavior in order to use this as an input to the DEM simulations. In pillars 3 and 4, this is where the physics and the simulation comes in. One of the key bottlenecks is understanding and collecting calibration data. The simulation relies not only on the individual particle properties of the actual material itself, but also specifically on the physics that we need to use to calibrate the contact models in the DEM simulations. So these are things like the static and dynamic angle of repose. So experiments in varying conditions need to be conducted in order to calibrate these simulations. These are then used in the DEM simulation, and using a surrogate model by using different neural networks for time and space resolution, we can increase the speed of computation by an order of 3, while still maintaining 95% accuracy within our simulation. This enables large-scale simulations. Here we can see a prototype model of the mini-ROXY funnel with the whole workflow of the UPREP methodology being applied here. Note here, this is still an uncalibrated system, and in the next slide I'll go into more details on how we plan to come up with these calibration data. We are adopting the diversity principle. The problem is, as I mentioned before, we can't just go to the moon. Of course, we'd love to have these calibration data in situ and in a standardized way. Here we can see the principle that we're adopting to disentangle the environmental conditions on the lunar surface from the mechanical behavior. So understanding which environmental conditions have which interaction or which impact for the overall mechanical behavior. In the Airbus lab, in the Regolith lab at Airbus, we're conducting flow breadboard experiments with a breadboard of mini-ROXY funnel. This is in ambient conditions and is a first step towards validating these UPREP models that I just showed before. We also, in collaboration with TU Munich, that have conducted parabolic flight experiments with Regolith simulants in order here to be able to extract the influence of the vacuum on the overall mechanical behavior. Avalanche tests are being conducted in Georgia Tech in collaboration with them. Here we're also investigating the influence of the electrostatic charge on the flowability of the Regolith simulants. We're in contact with the CREST lab, ESA facility, in order here to also observe the electrostatic charge from electrons onto the Regolith flow behavior. At the NASA Marshall Space Flight Center, the idea here is, again, different electrostatic charge influences on the flowability of Regolith will be able to be tested here. On the very right-hand side, you can see RAFT. This is a concept for a pre-lunar demonstration mission where the goal is to collect the calibration data in a very small and easy payload in order to have the necessary in situ data that we need to calibrate the UPREP models. Of course, throughout the whole value chain, one uncertainty is how accurate the models are when looking at Regolith simulants and comparing that to lunar Regolith. And of course here we're looking for collaborators and partners who have access to Apollo samples and data so that we can also use that in exchange maybe for the UPREP simulation data that we're conducting to forward this methodology. Currently, I mentioned so far 12 Regolith simulants have been scanned with the microtomography, and initial statistical models and particle generators are being developed and being improved currently. The goal here is to understand the microproperties of individual particles, understand the differences between the Regolith simulants, and also especially being able to understand the differences between the simulants and lunar Regolith so that we can also here quantitatively assess the predictive power of the models for lunar application. At the moment, I mentioned we have the flow breadboard test with the mini-ROXY funnel as a first validation for the mini-ROXY simulation we can see here. I mentioned DEM simulations are extremely computationally expensive. So here, surrogate models are being developed in order to increase this predictive power and increase the speed of the simulations so that we can use that directly to improve the design of mini-ROXY, but then for the future for any lunar architecture. For the future, we want to validate the surrogate models and apply, as I said, the UPREP models to a redesign of the mini-ROXY funnel so that we can de-risk this for the lunar mission in the future. With this, I would like to conclude. Thank you very much for your attention. I'd be happy to answer any of your questions.
Great. Thank you very much, Tehya. So we've got time for probably one question. I should have mentioned before, we were missing our second speaker, so we've got a little bit more time for all of the speakers today and some questions. So we've probably got time for one person. Roderick.
The sharing of information to calibrate your UPREP, is this open to anybody? when you work with simulants and do some tests, or is this a closed group?
I missed the first part of the question, I'm sorry.
You shared one slide where you say where the calibration data came from. Is this open for other companies that can join and share their data, or is this a closed group?
In general, we're open to collaborating with partners who have already conducted experiments in similar environments. This goes hand in hand with the diversity principle, so ideally there would be a give and take. So like we provide something to you, you provide something to us, so that we can try and standardize this calibration data collection. I think there's a lot of people at the moment and a lot of researchers working towards figuring out how to design lunar hardware, how to simulate regolith behavior. And so here it would be great to have this collaborative effort so that we can give and take and exchange ideas and exchange also information through the calibration data campaign.
Thanks.
All right, thank you, Tehya.
Thank you.
That's all the time we've got for this presentation. If you've got any further questions, please find Tehya at the break. So last round of applause, please. So our second speaker is no longer Alan Carter, but it will be Daniel Ricardo from Swinburne University. Is Dan here? No? Oh. Well. Maybe we'll move on to the fourth speaker, if that's possible.
I can just call in quickly. If not, I can jump in, because I'm like that.
Sure.
Yeah, we'll swap parts.
All right. Fourth, are you going to present instead of Dan? Or?
Yeah. No, I'm Philip.
Philip, all right. Perfect. Okay, fourth speaker then, Philipp Zanon from Swinburne University. We'll present instead. Sorry about that. All right, please take it away.
Is there a clicker? Cool. Hi, I'm Philipp Zanon. I'm a postdoctoral researcher at Swinburne University of Technology, and I'm going to talk today a little bit about the problems of lunar dust, some ways people have tried to solve it, the issues in trying to solve it, and some of the technologies we've come up with to mitigate against it. So you can see here, the moon is a very dusty place. And during the Apollo missions, there was a real, for lack of better phrasing, onslaught of problems that they encountered. Is that better? Okay, sorry. And there were many issues, particularly with the excavation tools. The telescopic pole jammed up. There were lots of vision issues. Thermodynamics was another big problem. Many issues associated with lunar dust that many people have presented on before, so I won't go into too much detail because I could spend hours on this. And it'll only get worse. So not only do we have to really think about what happens when we kick up the lunar dust and how does it get onto where we are, but the Lady mission also found that it exists in the atmosphere of the moon, particularly between the terminator zones. So the lunar surface has a charge environment actually between 100 and minus 4,000 volts potential difference in the extreme environments and extreme cases. And this then gave effect to what the astronauts described as the lunar horizon glow, which is likely what they think the Lady mission measured with the atmospheric dust cloud particles. And with this, the terrain also heavily influences how the dust behaves. So for instance, behind a crater wall or in a shadowed region, you will have a shadow. And within those shadows, you start getting what is known negatively charged dusty plasma. And these dusty particles will attach onto anything. And the same thing a lot of studies are saying will happen to infrastructure we put onto the lunar surface. where the shadows these objects cast will attract dust onto themselves, regardless of being stirred up or not. Now, parts of the characteristics of lunar dust that make it so difficult is that it's non-conductive, highly angular, and partially magnetic. And the things that really make testing difficult here on Earth to understand how adhesion affects it, or how to mitigate against the adhesion of it, is it gets affected by temperature changes, the vacuum that it's under, particularly electrostatic charge. We did a study as well, and we found that the simulant age actually changes how the particles electrostatically behave. So if you're using simulant for that's a 1-year-old as opposed to freshly ground up, you're going to get a completely different tribocharging profile and everything as compared to all the stuff you have sitting around in the lab. So there's been a few technologies that people have developed to mitigate against this. There's infrastructure solutions that prevent dust kick-up from rocket launches. There's technologies like the EDS, electron gun, which is what I think the next talk is about, surface coatings that prevent the surface energies, compliant mechanisms that just look at how do we survive the environment itself and just deal within it. And one of my favorites, the lunar lawnmower, which is more of a concept that NASA proposed. Brushes, and one of the higher TRLs up until recently, actually, and it was the wet wipes that the Apollo astronauts used. So we asked the question, why can we not simply prevent the contamination? And with this, we started looking at, okay, we have the electrostatic portion of the lunar dust. Can we use that electrostatic component to prevent the deposition in the first place? So the question was, can we manipulate the trajectories of these particles with electrostatic fields? And it means that we can circumnavigate the whole problem of overcoming the high adhesion that a lot of the current technologies aim to solve, and also target the really fine fraction of lunar dust that causes a lot of thermal issues. So when you're putting a point charge somewhere, to deflect particles of a single charge, you've got to solve a problem. That problem is, how do you get single charge particles to test with in a vacuum environment? So for this, we invented something called the electrostatic catapult, which is one electrostatic backing plate with a small high voltage launch wire, I call it. And you put the simulant in the middle, and when you create the high potential field between these two areas, you will separate out mostly the positive particles from the negative particles. So if your launch wire is negative, your positive particles will be flung out towards it. And this works quite well within the vacuum environment. As well, as you can see on the last image there, the chamber took a lot of cleaning afterwards, but showed it was a successful test. With this, then, we set up a bunch of deflection electrodes to see, okay, how can we, A, validate the model that we're developing, as well as see how the force field or point charge works. And when activating here, you can see an atmosphere that the particles, when they're not activated, will go straight through unharmed. But when it is activated, you can see how the particles are deflected away from the target area. And the way we measured a lot of this and then created a parallel twin was with a target slide. So we had a top, middle, and bottom section of this. And then we did our tests accordingly with the simulation as well as the tests in the vacuum to compare what the target slides and how they were behaving. And with the equipment we had, we were able to get very similar predictive particle deposition behavior and ratios of what the single deflection across the center middle plane was able to give versus what the attraction factors were. So it showed that we actually were able to manipulate the particles within a vacuum and that the model was fairly accurate to what was happening. So to show some use cases of what this could be used for is for the case where we have the natural lofting particles on the lunar environment. We can have a point charge put in the place of these particles, and we can prevent them from going into that area. This is particularly useful for when the Terminator regions here, or the natural dust that is around in the atmosphere, it will have mostly the same polarity of the charge. So we can reduce the amount of charge we deposit on the infrastructure this way. Then we looked at the case, pulling together several studies of what happens, okay, when you have a piece of infrastructure on the lunar surface, what happens with the dust naturally as it accumulates on the structure when there's a shadow cast behind the structure. So we have said, okay, reasonably minus 15 volt potential difference at the ground, and then the lunar base has a 5 volt potential difference, positive. And then we put simulated particles in different particle bins, some charges with also validated papers and everything. And then we can see that in the worst case scenario is what this scenario represents. The particles will come up and attract onto the lunar base, very similar to the other paper with the lunar structure in the introduction. And the convenient thing is if you put a point charge right at the bottom of that base of that structure, you can actually prevent a large portion of these particles depositing on the structure. And the nice thing is that this is an approach that could potentially work on the moon. It still has a lot of investigation to go with, but early tests and simulations show it has a lot of potential. Special thank you to my PhD supervisors that supported this project, Dr. Michelle Dunn and Professor Jeffrey Brooks. Yeah, thank you very much. And any questions?
Great. Thank you very much, Philip. So we'll open the floor to questions. We've got a few minutes, definitely, to answer any. Yes, up here. Yep, yeah, Mike's coming.
Well, did you encounter any practical reasons, not the reasons, but a use case to implement this on the moon in a machinery?
On machinery, I think a large issue actually is for implementing this is because there's a lot of driving and traction and turbocharging, you will get both charges of particles, similar to the issue you have with particle testing on Earth for this. So we haven't looked into it. I think if you, just from a quick test, it could probably make the problem a lot worse because you're then attracting particles onto it. The more use case for it would be static infrastructure. So like a high up solar panels where you can predict what the particle charges will be of the particles that would slowly deposit on that component or infrastructure or surface.
Yep, thanks.
There's a question in the middle.
Could you please, in a simple sentence, describe the generator and provide us with some idea on the power usage? Thank you.
Is this for the experimental apparatus or the
a demonstration product?
The point charge that, when I tested it in the lab, was about 2 watts of operational power.
Any other questions? Yeah, just back there.
Okay, that was not the mic. Thank you very much for the talk. Just one question, Robert Lindner, European Space Agency. You mostly looked at as dust shields, so as a, let's say, preventive measure, but have you looked as well at aspects of, let's say, dust mitigation once the dust is already stuck to the surface? Have you worked on that as well?
No, I'm currently working on a different project, which Daniel's going to talk about after this talk, where we developed an EDS system, which is good for the particles on the surface. The main reason for this project, or approach for it, was to investigate how we can prevent particle deposition, because there's a lot of research going on in what do we do with dust when it gets onto the surface. And then when it's on the surface, that's where a lot of the problems start. It's abrasive, it is hard to remove, the monolayers are really hard to remove as well. So I thought, okay, what do we do in preventing it? Removing it, not really sure, or haven't tested anything about it, so I don't have an answer for you, sorry.
Okay, thanks. So no work on, let's say, switching fields and stuff and using kicker pulses and
No, not yet.
no. Okay, thanks.
Got a couple more questions, maybe one more question. Yep. Oh, or over here, sure. We'll switch sides. Yep.
Yes, thank you for the interesting talk. I have a question about the last scenario that you have shown with minus 500 volts of charge. So in this case, it looks like you are flinging the particles away from the structure. So would you create a dust cloud around your structure with that while protecting the structure itself?
Potentially, yeah. So if you put it in a very bad location, you have a rover parked, let's say, off that chart somewhere, you run the risk of contaminating your rover. So that is something you do have to account for, is where you put these charges and then where, if you're preventing the deposition or manipulating the trajectories, where do you manipulate that trajectory to you not just put the issue somewhere else? Or maybe you want to put it somewhere else where it has less of a critical effect on your systems.
I see, thank you.
Okay. I think that's probably all we've got time for now. If you've got further questions, please find Philipp afterwards. So one more round of applause, please. All right, now we'll go back to our former third speaker, now our actually third speaker again. So Daniel Ricardo is here from Swinburne University as well. Would you like to use the podium or this one?
I'll grab the mic.
Sure, just hold it close to your face.
Hello, everyone. While that gets set up, sorry that I missed the talk. I was in an interview. This is my third talk of today, so I'm running back and forth everywhere. So Phil had a fantastic introduction for some of the work that we're doing at Swinburne University in Australia. So again, Phil's work is looking at how to prevent dust from happening in the first place, because a lot of dust mitigation technologies are trying to get rid of dust already contaminated surfaces. So building from some of the expertise, these are my slides as well. Could I get mine? Thank you. Building on some of the expertise that we have in the Space Robotics Group lab, currently we're working as postdocs on the Australian ROVER program. So ROVER is an Australian designed, built and operated lunar rover that will fly to the moon and operate by 2030. It's a consortium of about 21 companies from around Australia, and Swinburne is one of the project partners working on dust mitigation and radiation tolerance and mitigation. So this is some of the work that we're doing with that. Hopefully. It's the big green button, right? There we go. So a quick shout out to our supervisors. So Michelle Dunn and Jeffrey Brooks, and there's myself and Philip. So the ROVER program, a quick overview as well. Whoops. So here's ROVER with a kangaroo, hence the name, ROVER, and an emu, some Australian natural fauna. So ROVER is, again, a design, built, tested and operated in Australia and will operate by 2030. It is a technology demonstration of Australia's remote operations and surface robotics, so building on some of the heritage that we have from the mining industry. So it is part of the Australian Space Agency's Moon to Mars Trailblazer initiative, funded by the Australian government, which aims to accelerate the growth of domestic space in Australia. It is developed, again, by the ELO2 Consortium, which is 21 organisations from companies, universities and research groups across Australia as an Australian initiative, and Swinburne University is one of the project partners. So here's a quick map of the landscape of making it a national mission. So, lunar dust. I'm sure many of you know what it is and why it's a problem, so I'll be really quick. But I always like to tell people who aren't familiar, just imagine smoke that is composed of glass. So it's smoke-sized particles of glass. And I'm aware it's lithic and glass particles, but it just gets everywhere. It's really, really dangerous and poses lots of hazards. So here's a video some of you may have seen already of Firefly landing on the moon. And one thing you definitely see, all that dust. It's going everywhere. And this is going to be a persistent problem for all the lunar landings that we're going to have. And it's great to hear about the increased cadence and tempo of landings on the moon, but that just means more dust. So here's some analytical work we've got in a paper that's coming out soon, trying to quantify the impact of the change in absorptivity and emissivity of surfaces with increasing dust load for different expected dust cases. So how much dust is going to be on the surface, as well as the decrease in power generation. So this is just trying to quantify two main risks: how dust is going to impact your thermal radiators for your spacecraft, and how dust is going to impact your power generation for your solar panels. So one of the key solutions, which is trying to deal with an already contaminated surface, is quite well known, which is the electrodynamic dust shield, which is based on an electric curtain concept that was released in 1970, and it uses high voltage alternating electrostatic fields. So NASA recently deployed successfully an EDS concept on Firefly, so trying to get rid of all the dust that it kicked up. And here's a before and after showing a glass substrate and a thermal radiator. So again, thermal radiator and what would be used for a solar panel. RUVA. So one of the key risks, or I guess the design constraints that we have to deal with, is RUVA is a 20 kilogram Class D mission. We have very limited power, we have very limited internal volume, so we're trying to squish that all down into a functional device that works on RUVA, and there's some subsystem designs that we set ourselves. So less than 100 grams, less than 1.5 watts of power, and should fit smaller than in your hand. Timeline, it's super tight. So we've actually got a functioning prototype together in, I would say, a few months, pretty much this year alone. And we have a very, very tight deadline for trying to get a TRL-6-7 prototype done before the end of the year. So preliminary experiments, here's a breadboard that we made working under atmosphere on our bench. The electronics was about 150 grams, and we got about 60% of the dust clear in 4 minutes. So not great, but pretty decent. And again, this is flat. So one of the main benefits of using EDS is if you give it a slight angle, you're going to be pushing the dust off of the surface. If it's flat, it's just pushing the dust up and down. So just something to take note of. A brass board, so we made it 45% lighter. Again, we got the same clearing efficiency, but in a quarter of the time and for less power. So the top video is a test we're doing inside our vacuum chamber under ambient to make sure that it all worked. And then the bottom is it operating in vacuum. And I don't know if you saw at the start, I'll let it loop over. The dust comes off in sheets, and it just contaminated our whole chamber. So the impact of vacuum increases the efficiency of the dust clearing, which is actually quite good. So we know that whatever test we do under ambient, it'll be even more efficient if we do it under vacuum. And we did it at 10 to the minus 5 and about negative 20 degrees of the whole system. So again, we tried looking at tilting it. So the top panel is the breadboard. Now we're looking at bipolar. So not just positive high voltage, but bipolar, so swinging from high to low voltage, and it gets even more efficient because now we're dealing with both positive and negatively charged particles. And here's one of the first prototypes we got of a PCB, and you'll see as the dust is clearing, it'll show a message of, hey, we were showing Michelle, it works, we got it working in the lab. And she was very happy with that work. So again, by using bipolar alternating electrostatic field, we dramatically increase the efficiency, and this is a sort of a well-observed phenomenon in the literature. So some of the surfaces that we're able to make at Swinburne. So we have a nano fabrication laboratory which focuses on making nanophotonics, optics, solar panels. We actually in-house make these 2 and 3 phase, so depending on how many electrodes you want on your surface, on glass, so it's transparent. Our main focus is looking at getting dust off of camera surfaces, as well as doing flexible polyamide materials for thermal radiators. So you can coat this with thermal paint if you want, or you can put it on a secondary surface mirror if you want to get reflections. We made it on a PCB as well. So anything that is a common manufacturing product for PCBs, essentially, or photonics that we can use as an active surface for dust mitigation. So in conclusion, in a few months, we've developed a miniature, and it's going to get even smaller, 85 gram, 1.2 watt device capable of removing a large amount of dust under atmosphere and a cold temperature, not quite cryogenic yet. So future work that we're going to be, as soon as we fly back to Australia, because it took us 60 hours to get here. TRL-6 thermal cycle testing with Regolith simulant using, so we're also building an electron gun ourselves because electron guns are expensive and we don't have a lot of money. Going to be using that and a vacuum ultraviolet light to get positive and negative charge of the dust to see how does charged dust get cleared with EDS. As well as the work that Phil's been doing. So we're doing both sort of getting rid of contaminated surfaces and preventing contamination in the first place. And Swinburne also has quite a well-developed microgravity research field. So mostly for looking at cell cultures and how microgravity influences organics. So we have high school students each year coming and designing small payloads that go to the ISS, and that's an ongoing project to try and get more students engaged in STEM. And we're also looking at, for our brass board, increasing the bipolar functionality to increase the kilovolt range that we can operate at. So from 1.5 to 3, because higher voltage means you have more clearing potential. Reducing the weight even further, reducing the size, reducing the power, which we all want to do is the swap, the size, weight, and power. And then also optimizing electrode geometry. So there's lots of different levers you can pull to make it more efficient. So thank you very much. I hope you enjoyed the talk. If you have any questions, you can come find me and Phil after the talk. Thank you.
That was great. Thank you, Dan. Questions? Open the floor. We've got loads of time. So yes, please back there.
Hello. First, thank you for the talk. My question is, if it's over here, how well do you think it would cope with not being the uppermost layer? I'm thinking, for example, if there's a thin solar panel on top and then having it yours underneath.
So one of the limiting factors is the field strength is relatively very thin. So the moment you even increase the thickness of the dielectric, like in the PCB, the field strength decays rapidly with distance away from the electrode. So one of the things we were looking at is if we can put the electrodes underneath a surface. However, the effectiveness drops off dramatically. Because you have to put the field strength through that material. So ideally, you have this at the sort of the coal face, the exposed surface. You could just ramp up the voltage, but that means you have higher chance of breakdown, or your electronics need to be rated for that. You have potential charge dissipating in your sensitive systems. You have EMI, EMF. So ideally, you just keep things low voltage and very, very safe. But it could be something that we'll look at in the future.
Thank you. On this side?
Hey, Timon Schild, Ezric, thank you for your presentation. How are you planning to integrate that into your rover? Is the idea just to slap it on the side and work with whatever dust ends up getting there, or is there something more involved with actually putting some regolith on it and seeing then what you can do with it?
Yeah. So the main application that we can talk about, or the main application that we're using it for is for clearing off dust off of the cameras on the rover. In terms of integration and testing, we have a deadline to give them a functional part to do some testing by the end of this year. And then because the deadline to deliver the flight unit for testing to NASA, I think is later. In terms of the large functional system level tests, I don't have an exact timeline for that, but in terms of like functional subsystem tests, that's what we're doing over the next several months. In terms of like a functional system test on a low fidelity rover model, again, something that we can do over this probably next year. Yeah.
Yep, this side.
Yeah, again, Robert Lindner, European Space Agency. Thank you very much for your talk. Did you try different electrode geometries or only the spiral one?
So at the moment, we've done ladder 2-phase. We've done 3-phase spiral. Because we've had a very, very tight timeline, we haven't done any additional electrode patterns, but that's something we'll be doing the moment we get back. So I've already submitted the designs to the technician who does the fabrication of the transparent cells, and we're changing the electrode geometry, the electrode spacing, the thickness. When we do it, we're going to do like a test campaign to see what's most efficient, whilst also retaining visual accuracy, because you need to look through the electrodes as well.
Right. I have a couple of more questions, if you allow for it. At what kind of frequencies have you been driving the electrodes?
So we're focused on low power. So we're operating at about 1 hertz.
1 hertz.
Yeah. Okay. So you can, if you increase the frequency, you increase the cleaning efficiency. Yep. However, if you increase the frequency, you're increasing the power draw. And one of the main design constraints that we were given is low power as possible. Mm-hmm. So if it cleans at all and we can maintain that low power, that's more of a goal than getting really high cleaning efficiency in a short duration. Because the higher the frequency, the more quickly dust gets removed.
Right.
Yeah.
And I think one of the questions of interest is as well, how did you quantify the cleaning efficiency? Have you, let's say, in a repetitive manner, say, produced a certain obscuration factor, for instance? And how did you do that?
So this is
And how
building
did
off
you measure it? Yes.
Yeah, this is building off some of the work from Phil's thesis.
Yeah.
So we're using a laser scanner to do particle counting on the transparent slides.
All right.
So that methodology is already in a paper that Phil has published, I think. Yep. So we'll be publishing a paper on this year, hopefully, where we'll detail all the methodology of how we're actually quantifying dust clearing efficiency.
Okay, and last bonus question is, did you do it only on planar surfaces or as well on curved surfaces, since you specifically mentioned campus?
Yes, yeah. So right now we've only done a flat constrained surface. I would love to do a curved surface soon. I'm trying to think about how we can fit that geometry into our vacuum chamber and how we'd load it, because if you're just sprinkling on the top, you'd have a concentration in the middle and it wouldn't be even. One of the experiments we're trying to do, combining the research, is with the electrostatic catapult, fling charged dust onto a curved surface or a flat surface and see how efficient is the cleaning.
Thank you very much.
I've got time for one more question. Yes?
Hi, great talk. I'm Pollock from MIT and NASA. I had a particular question about the fidelity of your regolith testing. Is it sharp regolith simulant?
So all the experiments that were shown there was using LHS1 dust.
Okay.
Yeah, so the dust fraction that is commercially available from Exolith Labs in the States. We were going to look at using a range of different simulants to see how is simulants affecting our clearing, like the quantification of dust clearing efficiency. But right now we're just focused on getting a functional device ready. One of the previous talks in the previous session on simulants listed a range of the higher fidelity analog and simulants that could be available that include charge across the surface, the nanoparticle morphology and texture. Those all have dramatic impacts on the adhesion forces and the properties of actually getting rid of the dust. So yes, we'll definitely be looking at high fidelity analogs when we're doing the quantification of how good is it.
Okay. Yeah, my question was definitely about the sharpness and how that would affect how well it clears from your surface. Another question is, if I can do that. Okay.
Could you ask it at the break, actually? We're just got to move on to the next.
Okay, sure.
Yeah, come find us after the break. Thank you.
Thank you again, Dan. That's a round of applause. Right, our next speaker is David Asner from the Orbital Mining Corporation. If you want to use the walk-around one, use the one on the ground, but hold it close to your face. And also, just a reminder that if you'd like to vote for your favorite posters from the poster session, please go to the registration booth and let them know which one was your favorite. Thank you.
All right, good afternoon. I'm David Asner, Chief Science Officer for Orbital Mining Corporation. It's actually my first time to Luxembourg. I expect it won't be my last. All right, so today I'm going to tell you about the Lunar Scrub. Scrub is a bit of a tortured acronym. It's for Surface Cleaning Robotic Unit with Electron Beam. The picture in the upper right shows our electron beam device in vacuum. The short dimension on the electron beam is 10 centimeters, to give you a sense of scale. And there's a couple of GoPro cameras that are mounted to it. Yes, they did survive extended runs in operating in vacuum. And some of the photos that you see, well, all the photos and videos that you see will be from those cameras. And the distance you see to our sample plate, you can't see the samples, that's about 10 centimeters, 10, 12 centimeters. That's a typical cleaning distance that we used. All right, so I don't need to tell this audience, we've heard about it all week so far, that dust is a problem. So what did we do? We evaluated how well the electron beam removes lunar regolith simulants. We looked at various surfaces and several different lunar dust simulants. We played a little bit with environmental conditions. So all our tests were in vacuum. Electron beam needs the vacuum to function. And we tested some hot and cold temperatures, the limits constrained by the COTS components in our electron beam as opposed to the limits of our test capabilities. This work was done as part of a phase 1 SBIR. We just finished that at the end of March. And so the deliverable was to measure the efficacy of dust removal. There was a focus on things that resemble solar array components, so mostly flat glass surfaces. And we did receive several parts from companies that you're all familiar with for testing. All right, so this is another image of an electron beam. Same dimensions, this time without the aluminum foil on a cover and mounted to a robotic arm. I have no testing results with this robotic arm because it's not vacuum rated, and it didn't actually survive commissioning. So in the photo on the first slide, you may have noticed that the electron beam was actually mounted on a rail attached to an actuator motor, and that's how we simulated motion. So the goal is to develop a dust mitigation tool that's designed for tailored cleaning applications, complex geometries, the usual things we want to clean: connectors, seals, any mission-critical hardware. Solar panels has been a focus, radiators, anything where dust becomes a problem, and the obvious big applications are habitats, mobility vehicles, and of course, solar. And we envision 3 successfully more complicated concepts. So there's scrub fixed, which, as it sounds, is a fixed unit. You could think it be deployed as part of a solar array where it is dedicated to clean the glass on the solar array. A robotic arm mounted unit, or perhaps handheld, that's scrub mobile. And you could imagine that getting real-time feedback and adjusting your cleaning strategies using AI or algorithmic supported device, and that we call scrub intelligent. All right, so I guess let me describe the photos first. So these are some of our prepared samples to set the red construction paper behind the glass. The paper is just for contrast. It made it easier for the GoPros and then the subsequent offline analysis to work. 3 different Luna simulants. The dark one in the middle is JSC1. It really is JSC1. On the right is a Highland simulant from Colorado School of Mines, and the left one is LHS-1D, so it's the small stuff. First quarter this year, we did over 50 vacuum tests. As I already mentioned, none of those were with robotic arm. We did it with actuator motors, actually one on the sample tray and one on the electron beam. And the primary focus of all these tests was to measure the effectiveness of simulant removal. So we tested angles, not all things will be vertical. We did some tests with mobility, where either the sample or the electron beam removing. We picked a favorite configuration and did those tests over and over again to see if we got the same results. And then we did some stress tests with high and low temperatures. And the bottom line, you can see the top photo has dust on it. The bottom one looks remarkably clean, and from that, one might conclude that this technology works. All right, so I'm going to show you, hopefully, on the next slide, the videos actually work. They're clips from 4 videos. Every time we did a cleaning run, we took 6 to 8 minutes of GoPro video with it. So on the left is one of the very first videos that we took where we actually saw things work. We had a bit of a protracted commissioning period. So the focus is on the sample on the left. To set the scale, that's about 1 inch by 3 inches. There is glass there, although it's hard to see. The simulant's on the glass, not on the metal. So that's JSC1. And what you'll notice and so the electron beam is about 10, 12 centimeters offset. When the electron beam turns on, the dust flows and it actually looks like a fluid. And I assure you, the video is in real time. So that was actually kind of interesting and exciting because it was the first time we actually saw it really work. The second video, I believe it will be the second video, is the image on the top. And I guess your attention I want to draw to the sample on the right, which is the Highland simulant from Mines. And this one, rather than flowing off, really sort of puffs off in sheets. The third video, you can't tell, but that sample is actually lying flat. So it's horizontal. There is no gravity helping here. You can tell from the reflection of the electron beam that if the sample is flat, the electron beam is coming down like this. And you can see it if you squint for all 3 samples, but it's really pronounced on the JSC1, which is on the right, that it actually migrates, even though there's no gravity, in the direction towards the electron beam, which gives some hope that you could use this technology to have both a lift and sweep phenomenon. And then finally, it's one of our many repeatability tests, which shows all 3 samples being cleaned with pretty good efficacy. All right, so let's see if the video actually, is it running? Maybe now it's running. All right, so this is real-time playback. This is JSC1 on the left. And So that's real-time electron beam. I should mention it's about a couple hundred EV. The device is 20 to 30 watts total, and it looks like a fluid flowing, which we were quite surprised by. So now on the right-hand side, that's we missed actually the JSC1 getting cleaned instantly in the middle, but the Colorado School of Mines simulant on the right comes off in puffs. Sometimes tens of seconds go by and then another puff. This is playing back at 5 times the rate. All right, so the next one is the one that really surprised me, was when we had the sample deployed horizontally. So no gravity, but the lofting, and then clearly the electric field that's set up attracts the dust. So it's easy to see if you look at the JSC on the right. So this is flowing horizontally under the angular electron beam. So it gets swept across the surface without the assistance of gravity. And then last but not least, if you want to see these videos over and over again, a couple of my colleagues are staffing a table out in the exhibition hall, and Paulo Andrea can show you this video over and over again. And so the video is 10 times playback. It goes for about 6 minutes. We actually have photographs at the end of this. By 10 minutes, all 3 were perfectly clean. All right. So let's say something about the image analysis. So we actually did a pixel by pixel analysis. So the images are it's GoPro video, where we look at individual snapshots inside the video. If you take away nothing else, before cleaning is on the left, and 6 minutes in is on the right. And so one is very clean and the other is very dirty. We define what is a dirty pixel based on where the simulant happens to be on the sample. That's what's shown on the yellow. And then we prepared the samples, maintaining a clean region, which is the small yellow box at the top. And we used that as the reference to define clean versus dirty. And what's shown on the bottom is one of my favorite tests. This was actually with glass plates at 75 degrees. And over a 7-minute span, all 3 samples cleaned to better than 90%. So this is a pretty automated analysis. The code's written in Python and not by me. All right, so what do we aspire to? So this is our Dusty the dinosaur, not a reference to my age, but to the lunar environment. So we've demonstrated a prototype for Scrub Fixed. We will soon be developing Scrub Mobile, and Scrub Intelligent is somewhat in the future. What we've accomplished is we've evaluated electron beam removal using those 3 simulants, mostly across plate glass, but we've also explored more complicated surfaces. We did more than 50 tests, the commissioning program, testing at an array of angles, including flat. We picked a favorite configuration and did multiple tests to see if we got the same results repeatedly. And then we did some environmental testing. Specifically about the environmental testing, we successfully operated at minus 40 degrees Celsius, and that was limited by one of the COTS components. And we successfully operated at plus 70, again, limited by COTS components, and took it up to 100 degrees. We could go probably plus or minus 150. And we did achieve, as you saw in the previous figure, greater than 90% clean with all 3 simulants. All right, so what do we do next? So I think we heard yesterday that there's an RFI out from NASA. I say I submitted it last month. That's because I submitted these slides before NASA extended their deadline till Thursday. So the response to this RFI is still sitting on my laptop to be submitted tomorrow. And the purpose of this RFI is to propose that, of course, Lunar Scrub is on an upcoming Eclipse mission, and it would be integrated with an Intuitive Machines robotic arm. The Phase 2 proposal, which is due in 10 days, to continue this work, the primary focus of that is to integrate it with the aforementioned mechanical arm. And of course, in parallel to this, doing market research to figure out where are the best applications for our technology, continue to develop the product, and hopefully commercialize. And we believe we could be ready for CLIPS mission on the timescale of 2029. And with that, let me thank you and take your questions.
All right, thank you very much, David. All right, we've got some time for questions. Let's start on this side this time.
Hi. Don't know if this is on. There we go. Hi, Tyler Haynes, AVS UK. Obviously, there's a lot of variables involved, but have you been able to sort of characterize the amount of power required to clean per unit area, per unit mass of lunar regolith dust?
So we haven't done that rigorously. So depending on how we chose to operate this particular device, it was 20 to 30 watts, and that happily cleaned our area that was a few inches by a few inches. The beam kind of looks like a flashlight. There hasn't been a real attempt to optimize that yet, but that's about the right power. Because the real figure of merit is electron density on surface, and the sweet spot's about 5 to 10 microamps per centimeter squared. And so, if you want to clean a larger area, you need to use more power.
I think obviously, like you mentioned, it has particularly apt use cases for difficult geometries or difficult to get to places. I understand why it's a fairly high sort of power density for a small unit area. Thank you.
Great. This side.
Yeah, hi, Robert again. So my predecessors already asked the right question. Thank you for that. I have let's say, fallback question concerning the GoPros. Have you conditioned or prepared them for TVAC?
The short answer is no. We took them, we put them in vacuum. It was like, oh wow, they work. And after almost 3 months of continuous testing, they still worked. I confess they're getting a little bit flaky towards the end. For phase 2, I suspect we will procure new GoPros, but they worked really well in vacuum.
So it was mostly ambient temperature then.
So we did have thermocouples on them. They did cut out, or they would stop transmitting wirelessly back to us when they hit 40, 45 degrees. And so that was sort of what limited our 6 to 8 minutes of testing. So it was, how long does it take for the GoPros to get hot? And then they cut out. We learned that we unplugged them while they were taking data because charging the battery made them hotter. So so there's nothing magical about the GoPros. I was kind of surprised that they worked, but it was a nice solution.
So just COTS
yeah.
as is.
So what are they? Version 8, Chris?
We used 2. We used the latest version, and we also used 6.
Yeah, so I think we had 6 and 13. Yeah, GoPro 6 and GoPro 13.
Okay, so no discrimination whether there's a sweet spot in versions, which are the most suitable ones?
No.
Okay.
No, we haven't sampled all of them.
Clear.
Okay, what is cheap on Amazon right now is, I think, the criteria.
Thanks.
We've got time for one more quick question. No? Okay, well, thank you very much, David. That was great. One more round of applause. All right, our next speaker is Roderick Rühl from Polymac Space here in Luxembourg. Thank you. Please.
Hello. Hi. That was great with the camera. Thanks. Rod Rühl from Polymac Space. Let me just get the... Do I press play? I'm waiting. Okay. So if you've been here, not the first time, you probably know us because we've been sponsoring this event, I think, 3 years in a row. Yeah. And our background is... that's wrong. That's okay. I'm not. Yeah, let's go back. It's the wrong presentation. That's my lucky day. It's a Polymac Space. Fantastic. Thank you very much. So, yes, we've been sponsoring this event for the past 3 years. About the company, we build big things. It's a company that's been in business for 70 years in the bulk material handling business. That means we collect, convey, sort, and work with bulk materials. And the second generation owner of the company is also a space systems engineer, and then joined Space Resources Week, I think, 4 years ago, and had the idea, hey, I could apply my knowledge about the industry to space, Regolith. And this is how we got this unique spin-off, which is Polymark Space. They're based now in Luxembourg. I'm the CEO. My background is actually planetary science. Never worked in the field, and then worked 25 years in startups. So anything that you see here that happens in handling materials on Earth would eventually have to be done on the moon as well. So it makes absolute sense to take an industrial company from Earth and then to bring them to the moon. Because it's pretty much the same thing, with obviously the difference. I don't need to go into details that Regolith is slightly a special material, and that you need to find ways around it. So we went in there with a thought, oh, you don't have to reinvent the wheel. Turns out that you do. And if you look at conveying mechanisms on the moon, which is a problem that only a few people work on, you see that there are many ways, and they will make sense, but they are mechanically complex, and that is the biggest problem. You have to think business, you have to think long-term. It's super nice that you build something sexy in the lab, okay, that's complex. You bring it to the moon, it will fail, and it will fail, and you will not be able to repair it, and especially at scale. So you need to rethink how you convey. And this is how we came up with the concept of the modular drum conveyor. There's a patent that was, I think, signed in 2024. And it's basically a tube with a helix that is fused, and you have to drive the entire tube. You can see a video here that explains it very nicely. On top you have the conventional screw conveyor. It will press and push the material. At the bottom you have what we call the MDC. You see that the material moves in an entirely different way. It's pretty much, it keeps falling down. You push it up, it drops again, again, again. It also mixes the material. If you see what the screw conveyor does, it will basically just shift and squeeze it. And obviously, Regolith will start to eat away at the screw conveyor blades. Now we tested this. We have actually a lunar facility called the Moon in Germany, which is half the size of Luna. And we destroyed many, many blades there. The advantage of this is that it can be used for many ways. You can actually dig a hole through soft material. You can raise material. You can bring it onto a lander. You can attach it to a rover. Our job is to actually take this now and build as many components as possible in order to simplify what we called the Regolith logistics backbone. So we start with the MDC. We're building a sensor module that combines it with a lip sensor. We then sieve the material, and we can also preheat it, all inside the tube. That's the aim. Okay, so that in the end, we have this vision. So we actually got the trademark Regolith pipeline. And the idea is to really scale operations on the moon with this MDC. So where do we stand now? We've been doing this now for the past 2 years. We had a lot of things that happened last year. First, we were chosen as the SSP winner of last year. We've entered phase 2 with Esrik, starting now in April. We worked on raising material up. This is key. In industry, you always have to bring the material up so it can actually go through a flow. With gravity on the moon, you would have the exact same thing, but you need to raise the material. So one of the things we worked on is how to lift it. There are many ways in doing it. One you can actually see here. We have a lunar lander mock-up. And there's a technology that is actually already being used on Earth. We just fine-tuned it for Regolith by reducing the friction of the system. And as you see here, it works quite well. The problem is you need to fill the whole column. And if you lift Regolith up 5 meters onto a platform, it also weighs a lot. You have to press against this weight. So it is a good first version, and it works really well. However, we are looking beyond that. So this is what you see now here at the conference. But the MDC can also be used to raise the material up at an angle. 35-degree still works well. Beyond that, it's suboptimal in terms of consumption. But we are working at the moment to fine-tune this and get this better. So we are building and conceptualizing what we call a lander Regolith system. We want to allow Regolith material to be raised up onto a platform that it can be used by a range of payloads in order to reduce the cost. Now, one of the main costs that you have when you send something that has to touch the real deal on the moon is how do you get it on the ground? How do you place it on a rover? And the cost. So what we built would allow multiple payloads to have access to Regolith, fresh Regolith at the same time. Now, if you have a payload, you're interested in this, we're building a map to understand what the needs are and then propose a first mission. You can use the barcode. There's one here on the lander, and you can share your information with us. Then we worked with a range of institutions to see how can it be made. So the MDC ideally should be made on the moon. So we looked at a way that it could be made from Regolith itself. We melted. There's a cast that was provided by Fraunhofer IPK. We created a very rough form of MDC. I don't want to talk too much about this because actually the team is here and they have a poster. You can go and see them. We've worked with Fraunhofer IGP to also spray metal on the MDC to harden the tip, so it can be used also to excavate material from a mound. We are now working with DFKI in Germany, who won the ISRU challenge with their rover to see how the MDC could replace their bucket conveyor and a regular screw conveyor, and then compare how much better or cheaper or mechanically simple the system can be. That is something that we plan to finish by, I believe, September. So there we can actually directly compare how the MDC is compared to the standard means. We've developed a light Regolith that is 1/6 of the weight of Regolith, so it behaves mechanically similar, but it allows us to better understand the lifting, what we need in terms of power. Then, since we work with a lot of Regolith, we build these boxes. So if you have a need for a test box where you can work with Regolith, let me know. We built the system here on the left in the middle. We're going to launch the one on the right side, and it starts at about 8,999,000, so 9,000 euros approximately. This is the lunar test facility in Germany. This is our playground. It's open for business. We're really simple. You just say that you want to come, what you want to do, and then you can play around with the material, do your tests, and it's available practically anytime if you want to. So just let us know. That's the team. We are Polymark Space, and if you have the need to work with Regolith, to convey it, to bring it into your payload, then let us know. That's our business. Thank you very much.
Great. Thank you very much, Roderick. Okay, we've got lots of time for questions, so we can start over here.
Thank you, Mel Gelderman for Space Age VC. So, what kind of issues have you had with the rotary mechanism itself? Like, you show these boxes at the end of the conveyor. How's that working? And have you had any issues with Regolith? And then, secondary question. Have you also considered vibratory transport, and how does that compare against your current system?
Good question. So obviously the system is driven from the outside. Okay, so that's a key differentiator. So the dust is really inside the pipe. On the outside itself, there's reduced dust because the motion of the material is in the pipe. But obviously, it's a mechanism. At the moment, what we used are large cogwheels. That works quite well. It can get dusty. It's practically what you use in industry. And so far, we didn't have any problems. But this is in the environment here. But again, our goal is really to make it mechanically so simple that problems don't really emerge. One thing though, we do not at the moment work on the electronics. We just work on the mechanical systems themselves. Electronics, you have space-grade systems or components. That is not our specialty. We really work on the mechanical parts. And there, the system is actually quite safe in itself. So it doesn't need to be cleaned on the surface. It can be covered in Regolith. That's all fine.
And then against the vibratory, compared to a vibratory system?
Yeah, I mean, a vibratory system, we've been looking at this as an option to declog systems. Other systems that we work on, I don't think it's something that you can really scale on the moon. Our aim is really to move Regolith along long distances. If you look at the mock-up in the hall, you see that it moves material quite fast forward. And you really control also both the speed, but also the quantities, because the flight will actually determine the dose of each turn of the system. Yeah.
Thank you. Great. Go over here.
Hello. Okay. Francesco Latini, Italian Space Agency. So since the properties of Regolith being abrasive and the constant contact between Regolith and the blade inside your system,
MDC.
Yeah. Do you have some sort of coating for increasing the durability of the blade? And if so, how long do you expect the blade to survive or to be operative before you have to do some sort of maintenance to keep it operative?
Good point. So we've done with what I explained here, the metal coating, the metal spray coating. There we focused, mainly on the tip, so that it can also be used to excavate material on the surface. So at the moment we use space-grade aluminum, and because you don't have any moving components inside the tube, you only have the rolling motion of the Regolith. The abrasion is extremely low, so we haven't really seen any abrasion in the system on the inside.
I mean, there is though the Regolith is in contact with the blade.
Yes, but the blade does not turn. The Regolith is only rolling in a very slow motion. It doesn't really drive into it. I don't know if you've seen the system in the hall. Have a look at it. It doesn't really. There's no real pressure between or force between the material and the blade. Let me see. Here. You see? So the wheel at the top is turning into the material, so against the material, you have high friction. At the bottom, it's not moving. It just turns with the material at the same time. So, yeah.
Thank you.
Got time for one very, very quick question, and then we have to finish. So over here, either Philip or Dan.
Hey, Philip from Swinburne. I'm curious to when you say you want to put this on the moon.
Yeah.
How do you think, or do you think you'll handle the charge buildup from the turbocharging from all the particles?
Yeah, so that is actually the one point that we need, I think, help. At the moment, it's not a problem because we test against abrasion. We do expect that the particles will line, of course, the tube, but it doesn't fundamentally change what the tube does, the physics. Again, because you do not have a screw that turns against the tube. You don't have the moving parts. You have, of course, this coating, but in the grander scheme of things, it's simply not a problem. And that's the beauty of the design itself. However, for example, we have a sensor module in which we integrate a lip sensor that uses a laser through an optical window. And of course there, the coding is a problem that we need to solve. Yeah. And then for this, we need partnerships or somebody that has a ready solution. Yeah.
All right, thank you very much. That's all we've got time for. Thank you once again, Roderick. All right, our next speaker is Piotr Kulinowski from AGH University of Krakow. Do you want a podium or this mic?
Okay. Maybe if I see a screen, it will be okay. Hello. I'm waiting for my presentation. It was before, but it's still okay. Hello. It's pretty warm here, but right now it's much warmer than you because I start a very important presentation. I want to present my work and work of my student. I work as associate professor at University of Krakow, AGH, and I want to show you our project, Distoby, an integrated system for digging, storing, and beneficiation of lunar regolith. Yeah, it's our system on the moon, but not now. Let's start. Our presence on the moon and sustainable exploration of lunar regolith requires local resource. It means we have to use ISRU. We will use lunar regolith for construction materials, and also we need regolith for oxygen and metal. I'm worked for mining industry over almost 40 years, and I know that we need a robust machines working with in autonomous excavation and processes. Reason for designing our system was as a space resource challenge, and we developed our system for a special assumptions. The most important question what I asking every year is the capacity of our system. It is very important because it decides about our scale, about parameters, about everything. In this challenge, we had to collect and process 15 kilograms of lunar regolith. We have for this process 2.5 hours, and the energy budget was 300 watt hours, and the maximum mass of our system should be not higher than 60 kilograms. We have to dig, we have to transport, we have to store, and also we have to beneficiate this regolith in 3 groups. Granulation groups, it means depends on size of granulation, 500 to 1,000 micrometers, 100, 500, and below, for dusty material below 100 micrometers. And mine key design drivers was for us simplicity and reliability. And also we had to take into consideration the future work in lunar environment. Dystopy, what does it mean? Dystopy consists two main subsystems. It means for digging, we use the tube excavator. Also, we use the tubes for storing material and beneficiation. D, store, B, it means our system, but the B we add like the bees because of diligence, organization, and teamwork. The first component of our system is the digger. We use for digging screw heads, and we use tubes also for storing material. It's not AI generated, it's a real prototype, and I'll show later how it works. The second main component is a multi-desk screening unit, and we beneficate Regolith in 3 fractions. Between digger and sifter, we use a loading ramp, what you exactly see. Some words about concept of our system. The first step is, you see the scale of, this scale of our system. The length of our digger is 120 centimeters length. The height is half meter maybe. And we send our digger for Regolith. We mine them. And in the next step, the digger comes to the sifter. And the fourth step is to reload to the sifter and beneficate. Our project, I have to say that we made this project and prototype exactly for this challenge. We work on this project maybe 7-8 months from the ideas to the working prototype. And it was our idea to tubes which screw inside. This digger is scalable. It could be, we can use 4, 6 tubes, depends on capacity of our system. We mine, we dig Regolith, we storing in the tubes, and we use the rover to move the sifter. Very important feature of our system is that we have no silos. No silos, it means we have no problem with silos, with arching, bridging, funneling. We storing the material in the tubes, and we use the screw to collect more and to keep the material inside. Before building prototype, we build a test rig. I work with 2 students clubs. One is AJ Space Systems, specialized in rovers, and the Mind Space team, we focusing on the transporting devices for the moon and also for technological devices. We built in laboratory test bed, and on this test bed we have control box, computer, tubes from our Dystopy digger. It was the Regolith simulant from AGK 210. We have a measuring system with encoder, sensors, and what we measure? We measure excavator resistance, the work, we set up the parameters of work of our digging system, and also we can use this test rig for testing the wheels, driving wheels for our digger. You see the movies from this test, and we changed the auger rotation. That the auger rotation was 10, 15, maybe 20 rotation per minute, not 600. Before today I heard that it's possible, but in my opinion not. And we changed the digger speed, and we can find the optimal parameter for work of a Dystopy digger. And in this case, we have the maximum load in those parameters, but if you want to know more about our system, I invite you to our posters. We prepare 2 posters, especially with results of our test in laboratory. On the below, you saw the tests of traction properties of our driven wheel. The second component of our system is multi-stage screener. What is important, we use a brush system. Brush, it means we use the brushes on rotating arms for improve the efficiencies of our system. We add vibration, inclination. We test almost everything in our laboratory, but we decide to use the screens. It's probably a real problem, but we solve them. For reloading, we use inclination, and also the system works remotely with cameras. On this slide, you see our test on our test stand. You see how we sieve the Regolith simulant, and now you see a prototype with cameras. We all the time observe what happens during this process. It's very important that this sifter works in cyclic mode. It means for example, we use 10 minutes for sifting and 1 minute for unloading. We change rotation of our arms with brushes. It's a movie from our test. You see a laptop with cameras. We observe what happens. We dose the material like that from the digger. And result on the right graph, you see how many materials in specific fraction we got. But the quality of the process, you can ask my students next to the poster. They know exactly how efficient it was. Before we use our prototype, we test the monitoring system and control system. It was pretty hard, but we did it. It works in the Luna facility, ESA facility. We test the parameters, geometry. It was first meeting our digger and our sifter. And finally, we go to Köln, to the Luna facility. And we test our digger. It's not AI picture, it's exactly for ESA materials. And what we get? We get a stable rover mobility over the pretty hard terrain. And we dig enough material if we can. But we also had a problem, like usual in the space industry. We have critical software, sorry. Can I go back? Critical software with critical issue with software. We had the problem with the tilt for our tubes that I said we didn't want this competition, but we know why. We got a good lesson about reliability and redundancy of space systems. And finally, we're very proud of our system. Works perfectly. We know what's going wrong. We prepare for more tests in our laboratory. And we'll continue our work with Distal B system. I see that I over time. Okay. But thank you very much for your attention. If you want to ask, I'm open for discussion. Thank you.
All right, thank you very much. We've got some time for questions. Yes, on the left, my left.
Hi, thank you very much. Nice presentation. Upe with Polymark Space. I wanted to find out if your tubes can operate independently or they always have to operate simultaneously. And what's the maximum inclination angle and how does inclination angle affect your output or delivery of the product that you've stored or dug from the ground? Thank you.
Probably I didn't understand everything, but you asked about, in shortcut.
Okay, in short.
You know, it was a student project. It's ready for work, but not for the moon. But could you repeat your question?
All right. Can your tubes operate independently?
Yes. We have one drive unit for both screws with reverse rotation. But, you know, we are open for many solutions. It is under construction, still under test. That
All right, and the last question is, what's the maximum angle of inclination you're operating?
You ask about inclination for our digger, for movement, or for walk. We use inclination for tubes 15 degree. Okay. It was the optimum value, but we still saw that maybe we can use our tubes for drilling. But I have some ideas, you know, the space mining is still open for new ideas, but I still think about drilling. But, you know, below 30 centimeters, we have different regolith with different higher density, more problems.
All right, thank you very much.
Thank you.
Any other questions? Yes, back of the room.
Hi. So you said 150 kilograms in 10 minutes, right?
It was
the first
okay.
slide?
Our challenge was to dig a beneficate 15 kilograms in 2.5 hours. But our digger can reload in 1 minute 8 kilograms.
Under what conditions?
Yeah.
Under what conditions?
Work conditions? It
means it depends, right? What RPM of the screw it is, and then
yes,
what amount of cohesion is
optimum,
there?
yeah, in optimum work conditions, we can load in 1 minute 8 kilograms to our tubes and go to the sifter.
Okay, thank you.
Thank you.
Any other questions? Got time for one more? Yep, at the back middle.
Thanks. Hi, Joe Witchells from Esric. I was wondering, I see for the beneficiation system you chose to use sieves, so I was wondering, have you tested large amounts of regolith in the sieves to see long-term whether issues like clogging of the sieves might pose an issue?
No, we didn't test, but we have plans to test. We built a polygon and we want to test for long term. Especially we use the new solution with brushes for sealing our screw, for screen. We have to test for longer time.
Okay, thank you.
Thank you.
Any other questions? No? All right, thank you, Peter.
Thank you. I invite you to ask my students.
All right, our last speaker is Kamil Grassmann from Piotr Space. Do you want this one? Yeah. Just close to your face.
Hello, good afternoon. The best for the desert, I hope. So welcome everyone. My name is Kamil Grassmann. I'm CTO of the Piotr Space. Today I would like to present you our results in development of the dual-purpose drivetrain. This dual-purpose drivetrain was designed to collect the regolith, excavate, and in the same way provide the draft bar pulling force for the rover. So Piotr Space, together with the CBK, Space Research Center, has some agreement in the frame of which we are developing further this technology. So if we take into account the outline of today's presentation, so first of all, I would like to present our team. Nothing can be done without great team, dream team. Then I will explain you our motivation behind the development of the bucket drum. The next step will be, very briefly, I will explain the principle of operation of the bucket drum, the main feature of the system which we built, and the current validation status of the bucket drum. I will also present some brief test results. Of course, for the details, I welcome for the question after the presentation. And the last point will be, of course, our next plans for development of the bucket drum as a drivetrain for the mobile platform. So let's start. Nothing without the dream team. So you can see here that from very beginnings, our team loved to excavate, dig, and play with the desert. So here you can see the list of our team members for the digger bucket drum project. You can see here that I played the role as a system engineer and also technical leader. We realized this project for the ESA. Of course, everything what is from the ESA side, thanks to the Ginter Just who support us during this development. And of course, I will not explain and present all of the team members, but of course, nothing can be done without these great people. So if we take into account the motivation, we start thinking what we can develop for a reliable and high efficient system for excavate the regolith for big size, industrial size. So then we start thinking about two different configurations. The bucket drum as a payload, so you can see here on the figure RA, some quite common, I would say, configuration, but finally we also figure out that maybe the bucket drum, the system can be a part of the drivetrain. So in the same way, we can use the mass, the weight for the excavation system itself. So what was our constraints and some kind of requirements? The requirements was that the system shall be able to collect the regolith, the 15 kilograms of the regolith in one turn, and the mass of the system shall not exceed 15 kilograms. What about the power? Of course, for the lunar environment, the power is a tricky thing. So the requirement was that the 100 watts is the maximum power consumption which we can expect during the excavation, and the 50 watts was the average value which we should fulfill. Of course, during the project, we performed the development of the, let's say, preliminary design of the system for the real lunar environment, and then we focus on the mid-latitudes, taking into account mainly the condition, the thermal condition for the system. And of course, the most important, that the system should be high reliable. So if we take into account how the system works, and so here you can see the animation showing that outside we have the external drum with the scoops, which can rotate, and for the rotation is responsible the external motor. Then inside of the system, we have the basket, which is dedicated for collect the regolith, which is transported by the scoops. And inside of the basket, we have an internal shovel. This internal shovel has two functions. First of all, it's responsible for measuring the regolith, which was already collected. And on the other side, it is responsible for supporting the discharging process and how the system behaves. During the excavation phase, this cutout of the basket is located on the upper side, and then collected regolith by the scoops is transported on the upper part of the basket and fall down to inside of the basket. During the discharging phase, we're changing the orientation of the internal basket, and we also run the outside drum for removing the regolith from the system. On the left picture, you can see the cross-section of the system with some kind of simplicity, where you can see that, for example, sorry, where is the, sorry. So, where we have two motors responsible for movement of the basket and responsible for the movement of the shovel, and the motor responsible for movement of the external external drum with the scoops is outside of the system. So what is the status of the validation? We perform, let's say, almost fully campaign of the validation. So we perform the test in the thermal vacuum chamber, in the clean thermal vacuum chamber. So we not have the regolith inside, but we have some kind of MGAC to simulate the reaction forces during the excavation. And we perform the cycling test, thermal balance, and also the functional test in the hot and cold case. The system was able to survive all of these tests, so we passed to the, let's say, functional test in the dedicated test stand. So this is the test stand which we built for this project. This is the 3-degree test stand where we can put our bucket drum system. We can have the system is equipped with the offloading system, so we can reduce the normal force between the regolith and the basket and then the system to simulate the lunar environment condition, and we can perform the movement by 2 meters distance to check the behavior of the system and collect the reaction forces during the excavation. Of course, we also perform the tests in the PEL, in the DLR facility, with some kind of dummy, let's say rover. So this rover or the mobile platform has 2 passive wheels and bucket drum placed on the front axis, which can be also rotated to check the turning capabilities of the system. We also perform the dust tests in the ambient condition, in the atmospheric condition, using the analog of regolith, of course. So here you can see some movies showing how the system behaves and how it's worked during the test in the PEL, in the DLR facility. Here you can also see the movie showing how the system was able to overcome the obstacles during the moving. So all of the function was tested. We not pass, let's say, the overcoming the slopes with the higher level of the 5 degree, and that was mainly due to the fact that the motor which was selected for driving was not enough strong to be able to generate higher torque for that purpose. And on the last movie, you can see how this system behaves during this test on the 3 degree test stand in the laboratory. So what are the test results? We not exceed 100 watts in the peak. We were able to collect or achieve the efficiency of the excavation in the range of 124 kilogram per hour. And for that purpose, we use 15 watts for each collected kilogram of the regolith. We was also able to generate the draft bar pulling force in the range between 200 to 350 newtons. During all of the test campaign, we traveled around 5 kilometers without any failure or damage. And was able to collect in a sum of 350 kilograms during all of these tests. For all of the tests, we used 2 types of the regolith analogs. We use the AGK 2010, and we also use TUBS M analog. However, after the stripped down inspection, we also noticed that we have some kind of failure of the PTF seals, which we use in the system. However, on the other side, the good thing is that we also developed some new types of the labyrinth seals, which confirms its performance and work very well. And as I mentioned before, due to the negative margin of for the motor, for the driving, we were not able to fulfill the requirement about the requested slope higher than 5 degree. And the last point, what are the next steps? We plan to use the elegant breadboard which we built, but use some additional system with the mobile platform, which there we can control the slippage, because as I mentioned in the previous slide, the slipping between the bucket drum and the regolith is very important and has important effects in terms of the efficiency of the system. We also plan to perform the tests in the in Polish, let's say, facility or in the Luna facility, depends on the availability. So thank you very much for the presentation. If you have any comments, I am for the answers.
All right, thank you very much. We've got some time for questions. Anybody? No, it was a perfect presentation. You explained everything ideally.
Thank you very much.
All right, thank you, everyone. All right, so I'd like to thank our speakers one final time. That was the last presentation of this session. So thank you once again to everyone who presented today. The presentations were excellent. I think we all learned a fair amount about regolith, dust, and processing. So just a final reminder that if you went to the poster session yesterday, or if you've been looking at the posters for the last few days, to please go and register your favorite poster with the registration desk, because there's a prize for the best posters from the event. Otherwise, enjoy the coffee break, and we'll see you later on this afternoon. Thank you.